In today's lesson, we're going to look at the periodic trends in ionic size. So there are two types of ions. We have the cations and anions, and we'll look at both of them. Okay, we know that the cations are formed by losing electrons, and cations are smaller than the atom they come from. Metals form cations, and when metals form cations, they have the same configuration as a noble gas element, and this is true for representative elements only. So let's take a look at this statement a little closer. Cations are smaller than the atom they come from. So we're going to compare two different ones. We have sodium, which has 11 protons, and let's look at the sodium cation, which has also 11 protons. This one has 11 electrons, and this one has 10 electrons, and it has lost one electron. So let's write the electron configuration for this atom, which is 1s2, 2s2, 2p6, and 3s1. This one here is 1s2, 2s2, 2p6, and that is it. We have 10 electrons here. It has lost one electron. So let's look at the energy levels now. Okay, so we have the first energy level here, and then the second energy level, and the third energy level. For this ion, we have the first energy level and the second energy level. So let's draw the Bohr model to get a good representation of these energy levels. We have the nucleus in the center, and then we have the first energy level, and then we have the second energy level, and then we have the third energy level for this atom. For this ion, we have the nucleus in the center, and then we have the first energy level, and then we have the second energy level. Okay, so let's represent the electrons. So we have 1 and 2 here, and 1, 2, 3, 4, 5, 6, 7, 8, and there is only 1. The third energy level. This one, 1, 2, 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so now let's compare the size of these two, this atom to this ion. So we can see that this one has a third energy level and is bigger in size as compared to this ion, which has lost its electron in the third energy level and now only has two energy levels. So in this case, for the sodium atom, we have 11 protons and we have 11 electrons. So these 11 protons are holding on to these 11 electrons. In this case, we have 11 protons which are holding on to only 10 electrons. Therefore, the Coulombic attraction is more here as compared to is stronger. Since the Coulombic attraction is stronger, this nucleus is able to pull its electron much closer to itself, and therefore this is smaller in size as compared to the neutral atom. Okay, now let's look at this statement here. The cations of representative element. Sodium is a representative element. It is an A group. And would have noble gas configuration. So the cation here for sodium is +1. It has lost its one electron. Now it has 10 electrons. And if we look at this electron configuration, this is the same as electron configuration of neon. Let's look at anions. So we know that anions gain electrons. Anions form from non-metals, and anions are bigger than the atom they come from. So let's look at that statement. We'll start with it's the simplest atom, uh, fluorine. It has 9 protons and it has 9 electrons. And we're going to write the electron configuration for fluorine atom: 1s2, 2s2, 2p5. Now let's look at fluoride ion. It has gained 1 electron. It still has 9 protons, but now it has 10 electrons. And the electron configuration would be 1s2, 2s2, 2p6. Okay, so let's look at the energy levels now. Okay, so we have for fluorine atom, we have 2 electrons in the first energy level and 7 electrons in the second energy level. For fluoride ion, we have 2 electrons in the first energy level and 8 electrons in the second energy level. So to get a good representation of these energy levels, let's draw the Bohr model. We have the nucleus in the center, and then the first energy level and the second energy level. Okay, for this fluoride ion, again we have the nucleus in the center, and then we have the first energy level and second energy level. Okay, let's represent the electrons. One, two, and then 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. For this ion, we have 2 here, and then we have 8 electrons in the second energy level. 7 and 8. Okay, so for this one, for fluorine atom, we have 9 protons which are holding on to 9 electrons. For this one, we have 9 protons which are holding on to 10 electrons. So the hold of the nucleus on these electrons is less as compared to the fluorine atom. So the Coulombic attraction is less here, is not so strong, not strong as compared to this fluorine atom here. And since the Coulombic attraction is not strong, the nucleus is now holding more electrons as compared to this. So the hold of the nucleus on each electron has reduced. Therefore, this would increase the size, making the anion bigger in size as compared to this one. So this is bigger as compared to the neutral atom. Okay, so now let's look at the next statement. Okay, so the anions of representative element, and fluorine is a representative element, would have the same configuration as noble gas. So this anion here has the same electron configuration as neon. Okay, okay, so let's recap what we have learned. So ions of representative elements would always have noble gas configuration. So if we look at this example, this is sodium atom. This is the electron configuration of sodium ion, which is the same electron configuration as neon. Okay, and non-metals again would be able to achieve the noble gas configuration by gaining electrons, and that is true for representative elements. On this slide, we're going to look at the periodic trend of ionic size as we move down a group. So we're going to take a look at this example. This is from group 1. Okay, and they all are losing one electron to achieve the noble gas configuration. So as we move down the group, the size of the ion is getting bigger. And the reason it is getting bigger is because we are adding energy levels as we move down the group. Let's look at what is happening across the period. We know that the nuclear charge is increasing as we move across the period, but in terms of ions, between cations and anions, the energy level is changing. So let's look at this example from period 2. And lithium would lose one electron and would have this electron configuration of 1s2. Beryllium ion, to achieve noble gas configuration, it is going to lose two electrons and would have this electron configuration. Boron would also lose three electrons and would have this electron configuration. Carbon is a special element. It can gain or lose electrons. If it can lose electrons, this would be the charge on carbon ion, and this would be the electron configuration for that ion. Nitrogen, which is this one here, is nitride ion, oxide ion, fluoride ion, and we know that these have gained electrons to achieve the noble gas configuration. In this one, for nitride, it has gained three electrons. This is electron configuration for nitride ion. This is electron configuration for oxide ion, and this is electron configuration for fluoride ion. So we can see that as we move across a period, uh, the energy levels are changing between anions and cations. Okay, even though the nuclear charge is increasing, in this case, the nuclear charge is +3, this is +4, +5, +6, +7, +8, and +9. So the nuclear charge is increasing, but the number of electrons are different and the energy levels are different. So if we compare just the cations in this period, we know that as we move across the period, the size of the cation is decreasing, and the reason is the nuclear charge is increasing, and the number of electrons remain the same for all of these ions. The hold of the nucleus on its electrons is more, the Coulombic attraction is more, and therefore it's able to pull its electrons towards itself, decreasing the size of the ion. For this one, the anions in this case, the number of electron no, the number of protons are increasing, but they're trying to hold more electrons. As you can see here, there are 7 protons holding 10 electrons, 8 protons holding 10 electrons, and 9 protons holding 10 electrons. The size is comparatively very bigger as compared to the cation, but as we move across the period, the size is also decreasing for anions. And again, the reason is in this case for nitride ion, there's 7 protons holding 10 electrons, a lot more electrons. And in this one, for oxide, there are 8 protons which are holding 10 electrons and 9 protons holding 10 electrons. The hold of the nucleus is increasing, and therefore you can see the size of this anion is decreasing as we move across the period.